Hey everyone. So you see the title up at today. We're going to talk about arithmetic series. Now, we should be comfortable with the term arithmetic because we went through and dealt with an arithmetic sequence. Today, what we're going to really add in is the concept of a series. You'll see at the very top, there is your definition for what a series is. And it's going to sound way more official than what it really needs to be. But it's the indicated sum of the terms of a sequence. So, more officially, you look down below for the sequence, term 1, term 2, term 3, all the way up to term n. The sum of the corresponding series would be what you see in red and purple. There is your sum notation. It's an uppercase S and a subscript of n is equal to term 1 plus term 2 plus term 3 plus term... Okay, so if now I was to go back up to that formal definition, a series is the indicated sum of the terms of a sequence. Really all I mean by is you add up all of the terms. So rather than them being these separate terms within a sequence, all we do to make it a series, we add them all up. That's simple. Okay, with that though, we have a ton of new notation and some new concepts we have to consider. So we're going to take our time working into this before we even get to an arithmetic series. Take a look at what we have on our page now. We make a note for the series 1 plus 4 plus 9 plus 16 plus so on all the way up to n squared. You may have noticed that that sequence or series I gave you was made up of the sequence of perfect squares. I don't want that to be our focus right now. Really what I wanted to do, I just wanted to pick a sequence that wasn't arithmetic nor geometric. I didn't want you to get hung up on that aspect. So I just gave you a sequence that was perfect squares. I added them all together, so now it's a series. The question says, determine the sum of the first term, the sum of the second term, the sum up to 3 terms, I should say, and all the way up to the sum of 4 terms. So we should be able to do that pretty quickly. You can see that the sum of the first term is 1. And in a weird way, you actually came up with a little bit of theory. Like the sum of one term is always your A value. Like there is nothing else to add to it. Okay, let's not get hung up on that. We take a look at the sum of 2 terms, and for me to come up with the sum of 2 terms, I need to add the first 2 terms together. So I'm going to take 1 plus 4, there's my 5. For me to come up with the sum of the first 3 terms. Now, I might take 1 plus 4 plus 9, or maybe I say, well, I already took 1 plus 4 before, so now I'll just add a 9 to it. Then to come up with the sum of 4 terms, maybe you say, hey, I'm going to go 1 plus 4 plus 9 plus 16, but I'm going to bet and say that a lot of people would have just looked at that and said, well, I already did the sum of 3 terms. Let me get rid of that line. The sum of 3 terms in what I just highlighted in red, there was my 14. That for me to get the sum of 4 terms, all I need to do is add on the 4th term to it. Okay, I'm hoping we came up with the blue. And out of that, I want to kind of examine 2 quick little relationships. That coming up with the sum of the terms of a series, we don't just have to add up every single term. That if we do know some information, it can help us speed up the process. So if you take a look at what we see in red, that's what you probably did when you came up with the blue. That is, for you to go through and find the sum of 4 terms, you may have said, well, I'm going to find the sum up to 3, the sum of n minus 1, which you had already found. That was your 14. And then just add on term 4. So make sure that we're good with that red relationship, that I can find the sum of any series if I know up to the sum up to the last term, and then just add on the last term. Now, if I take that red logically, then I hope that we could also see that could lead us to the orange relationship. That if I have some information, and I mean some as in S-U-M, some information about a series, then I could find an individual term within that series by subtracting consecutive sums. So maybe we look at that one and we say, yeah, but like if I was going to look for term 4, well then term 4 would have to equal the sum up to 4 terms minus the sum that came before it. And you can do a quick check. The sum of 4 was 30, the sum of 3 was 14. You subtract those, there's your 16. That was your 4th term. So, not particular whatsoever to arithmetic nor geometric. Those properties relate to all types of series. Okay, what I want to do now, I want to jump into arithmetic stuff. So now what we're going to focus in on are specifically arithmetic series. And so for us, we should be good that an arithmetic series is then the indicated sum of an arithmetic sequence. And so we may be a little bit better equipped to deal with the concept of indicated sum. All that means is sum up to how many terms. Indicate for me how many terms you want me to find the sum of within a series. Okay, I want to jump into that by tackling a problem. So let's take a look at problem 2. Okay, there is our problem. We have to determine the sum of the first 25 odd natural numbers. Now, I'm going to lead you through this a little bit, because I think if I didn't lead you through it, this would lead to counting. And I don't want us to have us count. So what we're going to do is we're going to kind of walk through a process. If this was a problem I threw at you right now, and I asked you to try to solve it, then I think a great skill for you to have is to write down what the series would look like. Like, we won't write down the whole series, but we can get it started, and having that visual can help. So the problem asks me to come up with the sum of the first 25 odd natural numbers. So that means that I'm looking for the sum of 25 terms. There's my sum notation. Well, what would that series look like? Well, the first 25 odd numbers would be 1, 3, 5, 7, and we could keep going on listing all those odd natural numbers. But at some point, we're going to get towards the end of that sum, the end of that series. And so that might look something like a 45, and then a 47. Now, we may not know right off the bat, so how far does that series go? That is, what's the end of that sequence or series? Okay, let's say I don't know. What I'm going to do is I'm going to hop out for a sec, and I'm going to go on the hunt to find that. Well, I do notice that what I wrote in there represents an arithmetic series. That is, if I got rid of all of those plus signs in between and I just replaced them with commas, it would be an arithmetic sequence. And I know that all terms in an arithmetic sequence take the form of a plus n minus 1d. So I actually had the ability to find what the last number in that sequence is. I'm looking for what would be the 25th number in that sequence. So that sequence starts with a 1. I'm now looking for 25 minus 1 when I sub in my 25 for n. And I notice that my common difference in this problem is 2. I'm moving up by 2 on every term. Okay, I do a quick calculation. 25 minus 1 is 24. 24 times 2 is 48. 48 plus 1, 49. And so I know if I go back to that series, that 49 is my last number. There we go. Okay, that's what the question is asking me to do. It's asking me, find the sum of all of that blue. Now maybe you can see why I would say, hey, if I left you totally up to your own on this one, I think you would just count. But maybe you figure out a way to count quickly. I want to walk through just a little bit of a strategy we could use to go through and answer this problem. This may seem a little weird, but I'm going to call that equation 1. Now, that would kind of beg the question, well, then what's equation 2? Well, what I'm going to do is I'm going to make my equation 2 be the sum of those 25 odd natural numbers, but I'm going to write them in the opposite order. Like, notice, there is nothing in that problem that says, well, it has to start at 1 and then go plus 3 and then plus... No. To find the sum of the first 25 odd natural numbers, as long as I know my series has 1 at one end and 49 at the other, then maybe what I do is I write it in opposite order. Now I'm going to say to you, don't worry if right now what I'm doing makes no sense. Now I should say it should make sense, but if you're wondering, like, why am I motivated to do this? Then I would say, don't worry about that right now. We should be good, though, that what I just came up with is true. That for me to answer the question, I'm looking to answer the blue or the green, not both. Okay, so why did I do both? Well, if I use a little trick at my disposal, that is, I understand my equation work, what I could do now is I could take equation 1 and I could add it to equation 2. Now I know some of us, when we go to add some things, when we solve systems, we may like to put those lines across, like almost like a totaling line. You feel free, put that on if you like. Okay, what does that get me? Well, let's take a look at the left side. My left side now is going to be the sum of 25 terms plus the sum of 25 terms. That is 2 times the sum of 25 terms. And you may notice something really nice about when I add up the right side. When I add my first 2 terms together, I get 50. And then when I add my second 2 terms together, I get another 50. And my next 2 terms, I get another 50. And my next 2, another 50. And if I continue that pattern, you notice I get 50 again, and then a 50 again, and then a 50 again. That process actually may have sped some stuff up for me. Now, why was that useful? Well, my left side is still 2 times the sum of 25 terms, so I know I've got like double what I need. But at least I see on the right side that I'm going to have 50 a bunch of times. Like I'm repeatedly adding 50. Well, repeated addition is multiplication, so I could just multiply that 50 by the number of them I have on the right side of my equal sign. And if we go back to the original question, it was 25 odd natural numbers, then I'm going to multiply that by 25. And let's see how nice that becomes. That means that the sum of my 25 terms is really just 50 times 25 divided by 2. That is, I can get rid of the 2 times the sum of 25 and get rid of my times by 2 by dividing by 2. When I do that, I get to a nice little calculation that the sum of the first 25 odd natural numbers is 625. No counting. Nice. Okay, now you take a look at that process and you might look at it and go, I would have never thought to do that. And that's okay. I wouldn't have expected you to do that. You may have seen that, hey, if you take the first term and you add it to the last term, you get 50, and then the second term to the second last term, you get 50. And maybe we could shortcut some stuff that way. This process may not have been natural to you. But there is a process we can use to deal with any arithmetic series. Now, I want to come back to this in a little bit. That is, I want to jump in now and not deal with the specific series, 25 odd natural numbers. But what I want to do is I want to talk about any arithmetic series we could ever come up with. Okay, this is going to get a little ugly, and it's going to get a lot uglier before it gets nice and neat. But hang in there, okay? Okay, let's look at the relationship for any arithmetic series. Okay, there's our title at the top. We're going to do this for a generic arithmetic series. So what that means is we can't put in any specifics at all. As soon as we sub in a specific, then we're not solving it or proving it or finding it for any series. It's got to be generic. Okay, let's start building it out. So let's do the same thing we started off with. We are going to find the sum of n terms. What is our generic arithmetic sequence? Well, it would have a first term of A, and if it was a sequence, we would then put in a comma, and then an A plus D, and then a comma, and an A plus 2D, and a comma. But because we're talking about a series now, we're talking about adding those things together. So I'm going to have my first term plus my second term plus my third term, and I could continue that pattern on and on. Now, I don't know how many terms are in this series, so I'm going to put a plus and then a dot, dot, dot to show that there could be infinitely many, an unknown number of terms in between. And now this is where we might get a little ugly. Don't copy this down as we go because I'm going to alter some stuff. We should be good to know, though, that way down here at the end, whatever the end of this series is, has to be my generic term of a plus n minus 1d. So if we went backwards from there, then if that term was n minus 1, then the term that must have come before it would have to be 1 less n. So we would get a plus n minus 2d's. And then the term that would have to come before that would be a plus n minus 3d's, and so on and so on. So what I'm going to do is I'm just going to write that out. Now that we know what that is, it's a plus n minus 2d's. So maybe I'll give the second last term in the series. And then the last term in the series. And I just wrote n minus 2. N minus 1d's. There is my series. Okay, so now what did we do last time? We now took that exact same series and we just flipped its order. So rather than writing it in increasing order, let's call that, we switched the order. So the sum of n terms could now be that sequence flipped. So my last term, a plus n minus 1d now becomes my first term. My second last term of a plus n minus 2d's now becomes my second term. We don't see it in the blue series, but let's get it down in the green. My third last term of a plus n minus 3d now becomes my third term, and so on and so on. Now, to get down to the last two terms. Well, my second last term would have 1d in it, and my last term would have been the first term in my original, just an a. There is my two series written in opposite orders. That's all. Okay, now where do we go with it? Well, now we took that series and we decided to treat that like a system of equations. So we have equation 1 and we have equation 2, and we are now going to add those two equations together. Okay, here's where it's going to get ugly. We should be good that on the left side of my equal sign, I'm going to get 2 times the sum of n terms. Now, don't write this down. I'm going to do a little bit of rough work. But when I go to add the first term of the first series with the last term of the first series, so in flipped order, the first term of the second series, when I go to add together my two first terms, I'm going to get a plus n minus 1d. There is me taking the first and adding the other first. Now, you'll notice when I go through to add those two things together, the only parts that I can collect are my a plus a. And so that red would actually simplify to 2a's plus n minus 1d. Okay, when I go to do the same thing with my second terms in both series, I would now take the second term in the first one and add it to the second term in the second. Okay, I'm going to add those things together. I notice I can put my a plus my a together and I get 2a. Then I notice that I can put this 1d together with this n minus 2d's. So if I take 1d plus an n minus 2d's, then I can collect those things. I can collect on the inside, and I get n minus 1, and you can start to see the exact same thing is happening as what happened in our numbered example. That is, I keep getting the same sum every time. 2a plus n minus 1d. Okay, I'm going to erase all of that stuff I just did, because I now know what my common sum is. I get 2a plus n minus 1d. And then I'm going to get another 2a plus n minus 1d. And then I'm going to get another, well, I'm just going to put a little ... plus. And you'll notice we get the exact same thing at the end. Another 2a plus n minus 1d. Okay. I want us to put one other little note down on that line. Because if you look back at what we did on the other side of your page, the sum of the first 25 odd natural numbers, we took that common sum and we multiplied it by the number of terms in the series. Last time we knew we had 25 numbers. This time, we don't know how many numbers we have. Or kind of maybe we do. If I can get you to just write down right after that last, that what we have are n terms. terms. Remember, we are finding the sum of n terms. So if I was to then go backwards a little bit, or maybe backwards is the wrong way, but to take our next step, my left side is still 2 times the sum of n terms. But I now know that I'm going to take that common sum, 2a plus n minus 1d, and I can multiply it by n because I know it shows up n times. Now, some formatting. I'm going to write that m out in front because it is a monomial, and we tend to write the multiplication of a monomial out in front. Okay, now for me to solve for n, the sum of n, I should say, I need to divide out that 2, and we're going to tend to see it looking in that form. And there you go. That is, you now have a formula, a relationship, for the sum of any number of terms of an arithmetic series. You really want to be able to know this one. Like, know it. To the point where you want to write it down every time you use it. Drill it in. Okay, what I want to do is I actually want to go backwards a little bit. I want to jump back to that sum question that we did about the 25 odd natural numbers. And now that we know that formula, per se, let's use it. Okay, let's jump back. So what you see on the screen then is the work we did before when we didn't have a formula to use and we just kind of built it. What I'm going to do is I'm just going to kind of box this in a little bit. And I want us to answer this question a different way. Now, you want to look at the spacing I'm using on my screen because we're going to fit something else in a little bit later. But for me, now that I have my formula, I could say that the sum of n terms is n divided by 2 times 2a plus n minus 1d. And if I know my particulars about that series, I could just plug everything in. I'm looking for the sum of 25 terms, so I need 25 for my n. I can see that my a is 1, the first term in the series. My n was 25, I've already subbed that in, and my d was 2. Okay, I can calculate everything in there. Well, I'm going to leave the 25 halves because that doesn't divide evenly. Inside my brackets now, I'm going to get 2 plus 24 times 2, which was 48. And I come in on something that looks really familiar. Hey, there's my 25 times 50 divided by 2. And if I shrink that down a little bit, I can sneak in. There's my 625. So by having that relationship now, that formula, you have the ability to not have to go and rearrange and build, but rather you can just find the sum of anything you need. Nice. Okay, we're going to jump back to this part again, so I hope you left in a little bit of space off to the right. I want to take a look at the same thing, but from a little bit of a different perspective. So what I want to do is I want to take a look at what we did to build the formula of that. And I actually want to take that purple boxed in formula and I want to address an OR case, another case. So let's take a peek. What you see on your screen now in purple would be what I would call our sum of an arithmetic series formula. That is, you can take a look at it. That's the one that we built. N over 2 times 2a plus n minus 1d. What I want to do is I actually want to break apart that formula, though. And you'll see what I have in red is me just manipulating it. What I did was I took my 2a and I broke it back apart. So rather than have 2a, I have a plus a. Now, why did I do that? Well, I did that because a is just my first term. And you'll notice what I've underlined with my brace bracket in green That's my general term for an arithmetic sequence. That's the nth term, which means that's the last term. Now, why do I write it that way? Well, it's because if I actually change that red now, and I said that the sum of n terms is n over 2 times, and rather than using a to denote first term, I actually used my term notation and I said term 1. And rather than use a plus n minus 1d as my nth term, I called that term n. You actually might see another way to come up with your sum. And this is another way if we know different information. I'm going to take that red, and all I'm going to do is I'm just going to write it a different way. That rather than have the divide by 2 under the n, what I'm going to do is I'm going to put the divide by 2, let me get rid of that mess, under the term 1 plus term n. Now, when I write it that way, you can see that I do not need those big square brackets. And instead, I can write it like that. Now, what's the importance of that? Well, I'll be honest with you, I don't really like my green. I think it looks a little messy. So I'm going to just tidy that up. That's better. That if I was to put words to that, I could then say that what the sum of n terms is, well, I have its n times. Well, what does n represent? It's my number of terms. And I multiply that by me taking the first term, adding it to the last term, and then dividing it by 2. Well, anytime I take two things and I add them together and then divide by 2, I'm finding the average. So what I could say then is I'm multiplying that by the average of the first and last terms. Now, you will notice that this is a different way to get there. And for me to get there requires that I know what my last term is. But there may be a lot of cases where I can find that out, or it's been given to me. And so maybe this is the fastest way to come up with that sum. Okay, as I said, I want to jump back to a previous problem. I want us to examine that again. So let's jump back to that 25 odd natural numbers problem one more time. Okay, so you can see where we left off before, and I'm going to sneak in one more or. That this would be an instance where maybe I like that average formula. Like for me to come up with the sum of n terms, I could say it's my number of terms times the average of the first and last. So for me to come up with the sum of 25 odd natural numbers, well, that means I need 25 numbers, my number of terms. My first term is a 1, my last term is a 49. I want to find the average of those. And pretty quickly, we can see we're coming in on that same value that we've calculated a number of times now. That might be a different way to get to that sum. Okay, you take a look at what you have on the screen, and you have a bunch of different ways to get there. Now that we've proven a formula, we've built it and proven it, I would hope that you would make your blue your default. You need to be automatic with that. If we get into some special situations, then maybe the green helps us out. We always know we could go back and we could build it, but man, what a headache would that be if we had to deal with the red. So you make sure that the blue is your default and you stretch yourself into the green. Okay, enough for us building. What I want to do is I want to spend the rest of the time today just getting some practice, seeing how we use this stuff. Okay, let's jump into some quick problems. You see on your screen, you have to come up with the sum of the 30 terms, the first 30 terms for that arithmetic series, 5 plus 9 plus 13 plus 17, and so on. Okay, I think we should be prepared to be able to tackle this one on our own. So I want you to give it a shot. Pause the video now. Okay, we're back. So the problem says that it's an arithmetic series, and since you're asked to come up with the sum of 30 terms, then we should be good that we have a formula that does that for us. We've built it. I think it's a good start for you to say that you're coming up with the sum of n, and you want to write down that relationship every time and drill it in. So it's n over 2 times 2a plus n minus 1d. Now, the problem specifically asked for the sum of 30 terms. So you know your n, but we don't have our a and our d. Now it's your job to look back up to that series, figure out what those are. We should be good that our a value is 5, and when you look at how you move from term to term to term, you should see that we are adding 4 every time. So our common difference is 4. Well, plug everything in. So you're going to take 30 and you're going to divide it by 2. I am writing down this line just so you can see everything subbed in. However, I'd never have to see that. I don't think it's that bad to go 30 divided by 2 is 15. Calculate 2 times your a value. You're subbing in 30, so you have 30 minus 1 is 29. Calculate 29 times 4. Okay, we can do some calculations. You've got your 15 times, well, 29 times 4, well, that's almost 4 times 30. So that's 120. Take off 1 4, 116. Or maybe you do your 4 times 20 is 80. 4 times 9 is 36. There's your 116. I am showing way more steps than what I would need to see. Once you get everything subbed in, or what I think is a really good step, come in on that green star. You come in on that green star, and you can skip so many other things. Okay, we can calculate our 15 times 126, and then we're good. So we should have ended up getting a 1,890, and we should match up. And there we go. Okay, that's what we want to be default if we're asked to come up with a sum, and we've been given that information. You'll notice this one doesn't really work out so well if we wanted to use that average formula. Yes, we could have gone through and said, well, now I can find term n by a plus n minus 1d. So I could have found my 30th term by my a being 5, 30 minus 1 times my 4. So that ends up giving me my 5 plus my 29 times 4, which got me my 116, plus that 5, so 121. But what that gives me then is that my 30th term, all the way down here, 30th term, my last term would have been 121. And so what we could have done then is we could have said, okay, so my sum of 30 is my number of terms, 30, times the average of the first and the last. And so we get our 30 times 126 divided by 2. And you guys can see that we're coming right in on that line. I don't think that that makes you faster at all in this instance. And so for me, that's why I say I would make your blue, your sum formula, your default method. Okay, let's try another problem. Okay, this problem asks you to evaluate. And if you recall, the word evaluate means calculate. So you need to calculate what is 2 plus 5 plus 8 plus 11 plus blah, 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 plus 98, stop. So there is your series. You have to add up all those numbers that follow that pattern. Okay, you know that we're going to ask you to do this algebraically, so there's no counting. I want you to give this one a shot. Pause the video now. Okay, we're back. Okay, you take a peek at it, and I would hope that our first look, as I get rid of all of that mess, was you were taking a peek at it to try to come up with what type of series we have. We're adding 3, we're adding 3, we're adding 3. And so you recognize, hey, that's an arithmetic series. It has properties of an a value of 2 and a d value of 3. Our problem is that, well, we're looking for a sum, but I can't necessarily use my sum formula, any of them, because I don't know how many numbers are in that series. That is, I don't know what term number 98 is. But if I did know what that was, then I could go through and I could solve the problem. So I want to show you a stumbling way to deal with this. Perhaps you go, hey, I'm looking for a sum. It's arithmetic. I know that that's n over 2 times 2a plus n minus 1d. And then you start to sub in everything you can. So you go, well, I don't know my n, but I do know that I got 2 times 2, which is 4. I don't know my n, and I don't want to write it. It's like a blank spot. And I do know my d. Okay, well, I need to know what that n is to be able to answer the problem. Well, if you're stumbling your way through this, don't feel like you have to know where you're going at the very beginning. Feel free, hop out of your solution. Right now, I need to find what n is, so I'm going to go on the hunt for n. That means I really need to find out what term number 98 is. Okay, well, I do know that the general term for an arithmetic sequence is that. And so I can now find out what term number is 98 of an arithmetic sequence with an a value of 2 and a d value of 3. So I can solve that equation and figure out what n is. Get rid of my 2 and divide out my 3. Get rid of that minus 1. And I just found out that 98 is the 33rd term in that series. So what I could do now is hop back in, because I know that my n's are 33, and that the problem actually asked me for the sum of 33 terms. And you could work your way through in blue, and you could solve, or I should say simplify that whole thing. That becomes 33 minus 1 is 32. 32 times 3 is 96. That becomes 100. You can then multiply by your 100 and divide by 2, or divide by 2 on your 100 and get times 50. And so that's going to give us 1,650. And there we go. Hopefully not too bad. Now you will notice we had to do the orange. And if we had to do the orange, then you may have felt a little more inclined to use the old green. That if you saw from the very beginning that you needed to find out what term number 98 was, you may have then said, hey, I'm looking for the sum of 33. That is my number of terms times the average of the first term and the last term. And so now you have your 33 times 100 over 2, and you could have come in to your 1650 a different way. If you don't know where to go, then just start writing some stuff down Plug in what you know. Go on the hunt for what you can't or what you don't have. Feel free, pull out of your solution just as we did with the orange. And then when you find what you need, hop back in. But if we do know where we're going, then we're probably doing that orange first and then going to the blue or the green. Okay, let's tackle a bit of a quirky one, a bit of a doozy. You see our last problem for the day up on the screen. The sum of n terms of a series is given by the sum of n equals n squared minus 2n. And you have to determine term 10. Okay, I want you to play around with this one, and you play around with this one for as long as you need to. Then we'll hop back in and we'll check and see what we do. Okay, pause it now. Okay, we're back. Well, maybe the first hiccup could have been that you made an assumption that this was an arithmetic series. It does not say that in the problem, so please do not assume it. Don't segment your knowledge. So maybe that was your hiccup. You were trying to force it to be an arithmetic sequence or series. Don't. Okay, if we can make that correction, then pause it now again and give it a shot. Okay, we're back. So this would be one of those instances where, like, maybe I'm stumbling my way through and it says, like, come up with what term 10 is. Well, maybe I come up with what the sum of 10 is then. Like, you only gave me a sum formula. Well, at least I can do that. And if I come up with the sum of 10 terms, then that means I have to sub in 10 for n. And if I calculate that pretty quickly, I get 100 minus 20. There's 80. So I just found out that the sum of 10 terms is 80. Not term 10, but the sum of 10 terms. So if I was to write out that sequence, that series, like I'd have term 1 plus term 2 plus term 3 plus ... plus term 8 plus term 9 plus term 10. And if I added that whole thing up, then I know that that equals 80. Okay, maybe that doesn't help us very much. Okay, so where else could I go with it? Well, maybe you recall from the very beginning of today that we can find the sum, any individual term within a sequence or a series by examining the sums up until that point. So what I mean by that is, we just found out that if I add up all those red terms, I get to 80. Well, if I add up all of those terms that I just starred, that is the 9 terms that come before the 10th term. So if I found the sum of 9, then I would know what this total would be. So let me add up those 9. Well, then I can sub in my 9 for n. I get 81 minus 18, and that's going to get me a 63. Now, maybe you look at it and you go, okay, well, how is that useful? Well, if I was to write one more thing down, if I take that 9 terms that I added up, which was 63, and I now add to it term 10, then that has to get me to a total of 80, my sum up to 10 terms. Well, then that allows me to figure out term 10 has a value of 17. I found the term I was looking for. Now, if you're looking at that green going, where the heck did that come from? I know that it looks a little weird, but this is that relationship we started off the day with of saying 80 was my sum of n. That is equal to term n plus the sum up to what came before it, the sum of n minus 1. There's just a situation where we can use some of those quirky little relationships to help us through some quirky little problems. Okay, your job, get really, really comfortable with coming up with the sum of an arithmetic series, and as soon as you do, and it's automatic, then start playing around with some of those weirder problems as we go. Okay, best of luck.